meter P42. So here we have a Hall probe. It's a very slightly different drawing of the Hall probe than we used to see. Okay, and we place it inside a uniform magnetic field of flux density B. Okay, so I guess the magnetic field is coming. Not quite sure whether it's 90 degree. Let's see what the question says. Thickness of the slice is 1.8 mm. Okay, so this thickness here, X, is 1.8 mm. The number density of charge carriers in the semiconductor is this much. This is N. Constant current of 5.4 ampere is passed through the slice between the shaded faces. This is I. Hall voltage VH is developed between the terminals PQ and is recorded. Okay. So between P and Q, I connect a voltmeter so I can measure the Hall voltage. Cool. Figure 7.2 shows the variation of the time of B. So this magnetic field that we are, shooting into the semiconducting slice has a property that changes with time. So the value of B, probably changing the current, okay, will increase to 4 in 0.02 seconds, stay constant for another 0.02 second, decrease to 2 in 0.01 second, and then continue at 2 until the end 0.08. Okay, so your B changes. Show that when B is equal to 4.0 times 10 power negative 6, the magnitude of VH is 5 volt. So we can copy from the formula page. Hall voltage is BI over NQT. My version is BI over net. All right. Anyway, I just need to show the substitution. 4.0 times 10 to the power negative 6. The current just now was 5.4 ampere. The number density is here, 1.5 times 10 to the power 16. 5 times 10 to the power 16. The charge would be the electronic charge. So the electronic charge is 1.6 times 10 to the power of negative 19. The thickness here is given as X 1.8 millimeters. 1.8 times 10 to the power of negative 3. Okay, you could check your calculator. This will give you 5 volt. So pretty good. I mean, it's a nice mark just to warm up question. Now you are asked to sketch the variation of VH between 0 and 0.08 seconds. Okay, so basically this is the graph. How would VH change? So I want to do a quick sketch here first before I commit to drawing on the page. So the first thing I know is B is proportional to I. B is proportional to VH from this equation. The current is constant. The number density is constant because the same silicon. Q is constant and T is also constant because it's the same slice. So B is proportional to VH. So I will have the same shape. Let me copy the shape. That, like that, that, like that. This number 4 times 10 to the power negative 6 is the same as this one. So at this section, VH is 5 volt. Oh, so if you halve the magnetic field, what happened to the Hall voltage? Half the Hall voltage, lor. Very good. Okay. Okay, I can draw already. I just need to copy the graph. Of course, I gotta make sure the time is correct lah. So 0.02, 0.04, 0.05. Okay, I can do it. So using a pencil, it will increase to 5 volts in the first 0.2 seconds. Make sure it's exactly half or as half looking as you can make it. Okay, so it should increase from 0 to 5, and then it will stay at 5 with a sharp pencil. Again, maybe because I just marked my trial paper. Sometimes you all use pencil that haven't seen a sharpener that's having a long distance relationship with a sharpener. Can you sharpen your pencil before you go to exam? Don't bring a blunt pencil. And then it doesn't look like half. Then you lose a mark. Okay, so exactly half. And then it will decrease to 2.5, right? So it says at 5, then decrease to 2.5 at 0.05 seconds. Ooh. Let's try to draw 2.5. 2 is 2.5. What is 3? Half of 3 is 1, slightly higher than 1. It's kind of like you're drawing a quarter of a box. Best we can do is half. So right here, yeah, can lah. Right, then you steady at 2.5 all the way to the end. So I'm only drawing this 2.5 slightly above the 1 box line. Okay, your corner plots do not apply for your paper 4 theory paper. That is lah. And again, because I'm the kind of student where I think a bit one, meaning I think for the examiner. Maybe it's my people-pleasing tendencies. So I will actually extend my line here. Just like here, I will also extend my line because I will mark down the values for the examiner. It's not needed, but it helps my case because in case there is a difference in opinion about whether I draw at 2.5 or not, I mark 2.5. Hopefully it will mean something good for the examiner lah. But this one, obviously, I have the dotted line. Right? So this one would be 2.5, and this one is 5.0. Okay. It look like that. Sure, what's the purpose of the negative section? To confuse you. Were you confused? Were you like, maybe my graph should have some negative? There's no negative section in the graph. Okay. Teacher, I want to draw my graph entirely negative, can I? Sure. Why though? Okay. So let's mark the question. If there's a straight line from 0 to 5, this line is 1 mark. And if there's a straight line between two non-zero VH values, so any VH value, here is 1 mark. If this line is the same mark to me, meaning you copy the graph lah, right? If this line is 5 volt, it's 1 mark, constant at the correct position. If this line is 2.5 volt, it's 1 mark. This graph is 3 mark. Kindly copy the graph. It looks a bit squished because the scale is different. Negative is not needed. It's just there to cheat your feelings. All right, part B. We are now going to replace the Hall probe. So I think it's worth mentioning. Hall probe here is to measure B, since B is proportional to VH, which is what we did lah. We know the magnetic field is like this. We know the Hall probe will respond accordingly with the same pattern. Okay. But now we're going to replace with a small flat coil that has 3,000 turns. Wow, this is a lot of turns. The cross-sectional area of the coil is this much. The plane of the coil is perpendicular to the magnetic field. Okay. The EMF induced between the terminals is recorded as B varies as shown in figure 7.2. So B will go through the same thing. So one is to measure B, this small flat coil with induced EMF is to measure, is to measure induced EMF. But what we are measuring when it comes to measuring induced EMF is we are measuring the change in magnetic flux. So when we measure induced EMF indirectly, we are measuring dB dt. Okay, anyway, show that the magnitude of E at 0.010 is 2.0 times 10 to the power negative 4 volt. Okay, let's check out 0.010. 0.01 here. Okay, so along this line is the changing magnetic field. So along this line, B is changing. Okay, so I can take the gradient of this line. Let me write that down for you. Induced EMF is equal to the flux dt. You don't like this, you can write change in flux over change in time. But also, flux is equal to NBA. So allow me to continue with d dt. And you know what? For accessibility, I write both. For the maths people and the non-maths people, they mean the same thing, which is change. All right. The first order of business is to kick out all the constant because they don't change. N doesn't change, A doesn't change. What I have left is dB dt, which is gradient. Okay. N doesn't change, A doesn't change. What I have left is change in B over change in time. Okay. So hence, I can throw all the values in already. Induced EMF will be NA dB dt is the gradient of the BT graph. Okay, so from here, I can throw everything inside. This is 3,000. Area is 3.4 times 10 to the power of negative 4. Gradient of BT graph, let me stare at this first. I can take 2 divide by 0.01. Wait, got prefix more. Got 10 to the power negative 6. Sneaky. Two times 10 to the power negative 6 divided by 0.01. Okay, if you throw everything inside, you get E as 2.0 times 10 to the power of negative 4 volt. It's kind of weak because the magnetic flux density is very weak. It's micro Tesla. Okay, it's 2.04. The marks would be, you know how to state Faraday's law, something like this. There's one mark. rate of change of magnetic flux. And then you put in NBA gradient. So this line is 1 mark, or this line 1 mark. You throw everything inside and find answer. Is this overlapping? Okay. And finally, you're asked to sketch the variation of E between 0 and 0.080 seconds. So how would E change? This is 4 marks. All right, so here's what I know. I know that the graph consists of 1, 2, 3, 4 sections. Okay. In fact, if it helps, now I want to draw the induced EMF here. So you want to refer to the graph, and most of the time in exam, the graph grids will be side by side. So you can look at it side by side. Okay. So I want to draw the graph, and I'm going to doodle the graph here first. Quick one. So from 0 to 4 to 0.02 second, the induced EMF that we calculated just now was 2. Okay. Because it is the same straight line, so it will have the same gradient. Right? And then at this section is constant. So the induced EMF will drop to 0. It will drop to 0 until 0.04. Okay, and then it will change opposite. Opposite change means it has to be in opposite direction, right? So yoink, the negative axis. So can we compare the gradient of these two graphs, these two lines? Do they have the same gradient? Do I need to calculate again? You don't need to calculate again. Use the concept of gradient. This one took 5 small boxes to go up 10 boxes. Here, 5 small boxes to go down 10 small boxes. The gradient is the same, just opposite sign. 5, 10, 10, 5. One is going up, positive. One is going down, negative. Okay, so this one, the dot, negative 2. And then after that, constant lah. Okay, this negative 2 is not going to belong just until here. 0.05, and then after that, constant. So the shape of the graph will look like this. So, of course, you may be wondering, sure, wouldn't the sign be opposite because of Lenz's law? Like for example, when this B increase, shouldn't V be in the negative direction to oppose the increase? Yes, that is accurate. It's true, but they are not so finicky about the sign. So as long as this yellow and blue line are in opposite sides, is okay. But if you really want to follow Faraday, you need to flip the graph. Not Faraday. You really want to follow Lenz's law of electromagnetic induction to oppose it, then you have to flip the graph. Okay. So the reason why there is no negative here is because we are looking for magnitude, and most of the time, Lenz's law only come into play when we discuss the opposition. In the calculation, whether you show the negative or not, it doesn't really matter. Okay, so let's draw. So maybe I do want to show a negative. So I start with -2, opposition, -2, -2. And then at 0.02 to be 0, 0, 0, 0, 0. Then for this one, it will be 2, but at least 2 for half the time. And then here it will be constant. And as usual, I will extend the dotted line. And also, I mean, I'll draw full lines. Why not? 4 marks. Okay. Where are the marks? Why is this 4? Well, I guess because they considered the fact that you need to do a lot of thinking before you can commit to drawing. So the line showing non-zero E from 0.02 to 0.04, so here to here, and here to here, and E equal to 0 at all times. This is the first mark. They don't care about the value, but it cannot be 0. Okay. The second mark, top hat. Does this look like a top hat to you? This one lying on a person's face. More things, you know, Westerner things. I wouldn't look at this and think of a top hat. Okay, anyway, the shape showing non-zero E from 0.02 to 0.05. So I have values from here to here. Basically, the shape of the graph lah. Okay, you didn't draw some triangle lah. You did not, go like that. Shape of the shape of this and this is another one lah. The magnitude is 2.0 times 10 to the power -4 in both directions. So yay, yay, yay. So we'll check the graph. Okay. And finally, the sign of E is opposite sign. So it's either, this opposite sign either means this is negative, this is positive, 1 mark, or you could follow the sketch that I did just now, positive then negative, also can. Because they never tell me how they connect the voltmeter. So without that information, you want to show Lenz's law in the equation format, then you should flip the sign. This is the slightly more accurate one, but it doesn't jeopardize your marks at all. So that part, you don't have to worry first. Okay, so let's check out the ER and see what they have to say about this question. Okay, I want to start first with the first graph that we sketch, which is the VH graph. It says here, many candidates were blah, blah, blah. Okay, common misunderstanding is that hall voltage decreased to 0. So magnitude didn't decrease to 0, hall voltage won't decrease to 0. Okay, some candidates did calculate 2.5, but find it difficult to locate the value correctly on the VH axis. Now you know why I use a pencil? Because if 5 is half a box, 2.5 is quarter of a box. And I really cannot draw at one box one. I need to like slightly. Yeah, as accurate as you can make it. And then you hope for the best. Notice I didn't say this for your paper 3 or paper 5. Paper 5, you half a box. Okay, paper 4 theory paper, increased accuracy is expected. E is equal to d flux dt. If you want, you can flip the negative sign. Don't want, then don't worry about it. Okay, so your I, I'll open the S class one. Okay, all classes will have this page. It's in your notes. Okay, I thought about how you need to use Faraday's law to explain, calculate, but more importantly, to sketch the graph. So I, B, and flux and VH and VH will all have the same shape, okay? They won't have the same values, but they will have the same shape because they are all proportional. Flux proportional to B because flux is NBA sine theta. B proportional to I because of the mu naught Ni over 2R, okay? But also at the same time, VH is also proportional to, so VH will also have the same graph. So all these graph will be the same. Only induced EMF is the one that you draw the staircase graph because you are looking at the gradient of the line. So induced EMF is the shape as the gradient of IT graph or BT graph. or flux T graph. Okay, so we can see that calculation quite clearly here. Induced EMF is a constant times the gradient of the BT graph. I use BT graph because that's the graph I have. Like they give me another graph, then I adjust the equation accordingly, right? Use the question to help. And then after that, BH copy the same shape, hence proportionality. And then this one is the gradient.